going over what we have done the last time. The last time, the summary of lecture 4 is we had the relational principle in geodesic motions. And we discussed a few things about them. We started with the principle of least action or stationary action. And from this, we developed, which is that we have the real trajectories picked up by the laws are ones that minimize mostly some action. And the action is an integral over the path of some function depending what we call the Lagrangian, depending on the point and the velocity on the path. Then we derived Euler-Lagrange equation for such motion. That means you can describe this principle which tells you some kind of global choice between different trajectories, replace it by a local equation, which is in some sense close to second Newton's law, because it has some kind of second derivative is given on the trajectory. Then we have seen in this particular case, when you have Newtonian dynamics, then the Lagrangian is the kinetic energy minus the potential energy. And we told that this is not so physical, such expression. And really we want to get some more meaningful Lagrangians, and our theory will try to give them with more meaning. We have seen free motion is given by straight lines in space-time, and straight line in space-time has several equivalent properties. One of them is the shortest route between the 2 points. And when you want to generalize it, this helps us to generalize it in case when the space-time is not flat. That I introduced a generalized principle of inertia. The reason for it was that really we are talking about, physics talks about inanimate objects. They have no way how to change their velocity. So they try to keep their velocity. They will keep their velocity under their motion, but they are influenced by different forces, which generates them their own world. And their motion is given by geodesics with respect to this world. And we'll have to learn how we describe the world of different, influenced by different forces. We started with an illustrating example, which was at the shortest part on the globe. That means you have motion you want to reach on the globe from one point, from the origin to the destination. When we want to do this, we want to go in the shortest way. In the way when we are inside the system, we feel we go straight. And the airplane flies from one point to the other. There's no reasons why I had to go not straight. He can put it on autopilot, keeping the velocity, and he picked up the right direction to reach the destination. But when you look on the globe, we get the path doesn't look straight, and we had a way how to describe it. That means to describe it, we have to have a map, which is to a way associate any point in the space. I have to. Okay, and then to associate for each one a point in the space, point on the map. The map is flat. And then you have to be able to translate distances from the map to reality, which is what is called a metric. And then the shortest route is with respect to this metric. And today on the exercises, we explain a few examples to make it more concrete. And then we discussed another example. When the geodesics motion is given by some metric, that means we have, that's the the general outline for relativistic Newtonian dynamics, we are describing everything on a flat space-time. What is this flat space-time? Is like we took an observer sitting outside the system, or if we are inside the system, we are referring our position with respect to objects which are far away. It means we are measuring like on a map, not feeling. What would be, that would mean no field. And then we define the metric caused by the field, and then we find the geodesic motion. Now we explained why we need an affine parameter. We saw that in this case, we know what is the geodesic. The geodesic is the shortest route, and which is the analog of a straight line in flat space-time. That's the natural assumption for being the Lagrangian. Lagrangian is something that will measure what is the closest short route. And in this case, we found that in order to have only one parameter describing the evolution and to get second derivatives by this parameter, we need that the parameter be proportional to the metric. That was very important conclusion. We will use it today. Then we have seen an example, Snell's law, propagation of light between two different media, and we found the bending of light follows nothing more than conservations of the momentums, which follow from Euler-Lagrange equation. Euler-Lagrange equation provide us a different conservation laws, and which are in turn, they help us to solve problems. So then we had a few exercises. I'll turn it to this card to continue with the exercises.
Okay, so here we go with the solutions from lecture 4. So the first problem was to derive the conservation of angular momentum for a central force using the Euler-Lagrange equations. In the second lecture, we had seen that angular momentum is a vector defined this way, r cross r dot, which is the same as r cross the transverse velocity, since any velocity that's in parallel to r doesn't contribute. And the magnitude of L is m, you multiply these, m r squared lambda dot, because the transverse velocity is r lambda dot. So this is what we want to show is conserved. We form the Lagrangian. Here we are using spherical coordinates, so the velocity squared appears this way. It's the sum of the radial velocity, r dot squared, and the transverse velocity. Minus the potential energy. Now we apply the Euler-Lagrange equations, which we see up here in the box. We differentiate L by R, and we'll get this expression from the kinetic energy. And then when we differentiate the potential, we'll get the force. And the expression in parentheses is exactly the transverse velocity squared divided by r. Now we have to differentiate the Lagrangian by r dot, and we get simply mr dot. And Euler-Lagrange tells us that the derivative of this, mr double dot, must be equal to this expression. So we move things around and solve for F, and we have a nice equation of motion for a central force. The force is the mass times this expression, which is a combination of the radial acceleration, r double dot, and the centripetal acceleration. This part really doesn't have to do anything with the angular momentum, but it's nice to see what you get when you use r and r dot. You get the equation of motion. If we'll take this Lagrange, well, let's talk about the simplifying a little bit. Let me go back. We can assume that the motion is in the plane because think of the plane that's spanned by the initial position and the initial velocity. Since the force is central, so the force also is in this plane, and therefore the motion remains in a plane. So without loss of generality, we can take the plane phi equals 0, which is the equatorial plane. And then the Lagrangian reduces considerably to this expression. We differentiate by lambda. It doesn't depend on lambda, so it's 0. Differentiate by lambda dot, and you'll get mr squared lambda dot. So this quantity is conserved. It's exactly what we wanted to show. Okay, the second question dealt with geodesics on the globe, on the Earth's surface. And we want to find the shortest path between 2 points, an origin and a destination. We'll use this metric, which we saw last week. And the Lagrangian based on this metric is this expression. And we take the derivatives by phi, phi dot, lambda, and lambda dot. Here I'm assuming that the radius of the Earth is 1. It doesn't really play a role. It's a constant throughout. So you get some kind of complicated expressions for these derivatives. But in simple cases, for example, if phi would be constant, so this expression is 0, and if you take phi equals 0, this expression will be 0. In order to find the geodesics, we have to prove the following claim that on a sphere, the geodesics are great circles, which means circles on the surface of the sphere which go, the plane of which goes through the center of the sphere. How do we prove this? Consider 2 points that lie on the equator, which means the latitude is 0 for both. You can form a very simple path which will take you from one point to the other, stay at 0 latitude, and just linearly progress from one longitudinal line to another. And when you compute the derivatives, you get the following equations, and therefore Euler-Lagrange is satisfied. The derivative of this is also 0, which equals this one, and the derivative of this one is 0, which equals this one. Now, intuitively, why should we be looking for great circles? In the picture, we see 3 circles, all of which go through these 2 points, this one and this one. Which circle is closest to the straight line between them is the green one, and he has the largest radius. The bigger the radius, the closer this arc will be to a straight line. Let's look at an extreme example on the globe. You want to go from a point in Alaska on the Arctic Circle to a point in Sweden on the Arctic Circle, which is about 66 degrees north latitude. Well, you could go all the way around this way, keeping the same latitude all the time. But you can show that this distance going straight over the North Pole is much shorter. And in fact, the direction from this point A of the geodesic is towards the North Pole. In general, it'll be a different angle. What about, for example, going from New York to Madrid? They're both 40 degrees north latitude, approximately. So if you wanted to leave New York and go and stay on the same latitude, this would be your path, the purple dots. But maybe there's a shorter path going this way, and you'll get to Madrid sooner. So let's see, how do we calculate such a geodesic and the direction to go, and how do we measure the angle between this direction and the direction to the North Pole? So we put in the longitude and latitude for New York and Madrid. Now the V1 is, for example, a vector from the center of the Earth to New York, and V2 is from the center of the Earth to Madrid. They lie on a great circle, which is a plane through the center of the Earth. And we want to find this tangent vector at New York, which is a tangent to this great circle. So how do we do it? First, we form the cross product V1 and cross V2, which will give us a normal to the plane of the great circle. Then we do another cross product. We cross product the cross product of this vector with V1. That will give us something in the same direction as this tangent vector, and that I call that the geodesic direction. Now we want to measure the angle of V with the direction to the North Pole. So we take a unit vector pointing north at the origin city, in this case, New York. And then the angle is simply using straightforward linear algebra, that the dot product is the product of the magnitudes times the cosine of the angle between them. You plug in all the numbers and let Mathematica crunch it out, and we see that the angle is 65 degrees, which means that if you want to leave New York, you should take an angle that's 65 degrees from due north, so about 25 degrees from the due east, and you'll get to Madrid the fastest way. Okay, and the last problem was to find examples of the generalized principle of inertia. Think about a cabin in free fall, sometimes it's called Einstein's elevator, freely falling towards the earth. So inside, you float in the air. You don't feel any forces around you. You throw something and it just continues in a straight line until it hits the wall of your cabin. And you're no forces at all. Even though from outside, somebody on Earth sees you accelerating quite rapidly. And then a spiritual example from Proverbs, educate a child according to his way. Each child has his own particular traits, characteristics, character traits, has his own way, and a good father, a good parent will perceive each child's way and learn how to work in the child's particular world.